Adwa.
Nsuodia.
Yeah, very quiet. She won't talk. Shame on to you. Okay, so if you give it a small angular displacement, this will be the displacement equation for 2 cycles. So this is for small angular displacement. Now, when you give it a large angular displacement, which we don't encourage in practicals. In practicals, we always ask that give the body small angular displacement. This is what happens. The body starts with a large amplitude. So you realize that this amplitude, you see over here, the amplitude is uniform. Same amplitude, up and down, same amplitude. But when you give it a large angular displacement, it starts with a large amplitude. Then as time goes on, the amplitude drops. The amplitude drops because the energy transferred will not be consistent. Then this is what will happen when you give it a large angular displacement. It said the oscillation dampens. Oscillation damps. So that is what will happen when you give it a large angular displacement. As the body oscillates, then it will be losing energy. So the initial amplitude of oscillation very large. But as time goes on, you realize that the amplitude reduces. There's the initial amplitude. There's the, you see, so you realize that as time goes on, the energy will be lost and then the amplitude will be reducing. So this is when you oscillate a simple pendulum for 2 cycles and you give it a large angular displacement. So that is the reason why we ask that in practicals, when you are displacing it, give it a small angular displacement theta. In that, with that angle, the oscillation will be uniform. The energy will be constant, but this is it. Please, are you okay?
Yes, please.
Priscilla, I won't also then. Okay, the old request. Now let's look at the velocity. Can I clean this? Can I clean it? This one.
Yes, please.
Yeah, I'm crying my paper. So the velocity of a body in simple harmonic motion. So velocity of SHM. Yeah, last time we realized that under linear motion, circular motion, velocity is the rate of change of displacement with time. So dy over dt. Meaning that if we want the velocity of the body, okay, doing SHM, why velocity? We see that as time goes on, the body will be oscillating around. Let me demonstrate something. So this is a loaded spring. This is a loaded spring. This is the load. A spring connected to it makes it a loaded spring. When you oscillate this, at one point, this is it. This is the equilibrium position is somewhere here. So at one point, you realize that the body will start and then another point move. So its displacement is changing with time. Okay, across the equilibrium position. Let me push this here. Good. So the marker is the equilibrium position. Okay, so you realize that with time, the body's displacement around the equilibrium position changes. So if the displacement is changing with time, then there is velocity. At one point, the velocity is zero. Another point, the velocity is maximum. That is what is the characteristics in an oscillating body. Every time its displacement is changing. So if its displacement is changing with time, then the body is said to be having different velocities. So if the body is oscillating around, at one point the body is here. This is its displacement. At another point, the body is here. This is its displacement. Okay. At another point, the body is here. This is its displacement. Then at another point, the body has gotten to this point. Then its displacement is equal to the amplitude A. At another point, it is here. Okay. So this is its displacement. At another time, the body is here. This is its displacement. At another point, the body is here. Its displacement is equal to the amplitude. So at different times, the displacement of the body is changing. So if we differentiate the displacement function with time, we get velocity. So to obtain the velocity equation of a body in simple harmonic motion, differentiate the displacement equation or function. Equation or function with respect to time t. So that is why we are saying V is equal to dy on dt. The dt, the dd indicates that differential of y displacement with respect to time. Class, are we okay? Are we fine?
Yes, please.
Adu, are you fine?
Yes, please.
Deborah Bessa Hoodie, very quiet. She won't talk. So A sine omega t with respect to time. And last time I showed you the differential of this. When you differentiate this is a coefficient. It never forms part of the differential. But this is also a function of a function. So you differentiate the daughter function. When you finish, you differentiate the mother function. The daughter function is omega t. So what is it? Omega t is the daughter function. And then sine omega t is the mother function. So you differentiate the daughter function. When you finish, you differentiate the mother function. Okay, so let's first differentiate the daughter function with respect to time. So del dt of omega t times del dt of the mother function sine omega t. So when you have a function of a function, this is how to differentiate it. You differentiate the daughter function, then you differentiate the mother function. A differential of omega t is equal to omega, because this is omega out dt on dt. I'm applying mathematics, so let me use it. When you get there, you'll be taught. Then the differential of sine omega t is equal to cos omega t.
Mr.
Hello, Mr. Helder.
It's first time. Mr. Dida, please, where did you start from? Like, I don't understand.
Where?
The differentiation.
It's we have constant differentials of trig functions. When you differentiate a sine function, it's equal to cosine. So if you have y is equal to sine theta, and you differentiate the y on the theta, it's equal to cos theta. Then if you have a cosine function and you differentiate, the differential of a cosine function is equal to the negative of sine. So a rule formula may apply, right? I'll send them to you so that you learn. Okay. Because you haven't done it in maths, that's why. But so I am borrowing it. So dt, they'll all go and drink tea. They've cancelled out. So the differential of the velocity function, therefore, is equal to a omega cos omega t. So this is the velocity function of a body doing simple harmonic motion with respect to time. So v is equal to velocity equation or function of a body doing in simple harmonic motion with respect to time. So this equation is with respect to time. We would later derive another equation which is with respect to displacement. Okay, so put this at the velocity function of a body doing simple harmonic motion with respect to time is equal to a omega cos omega t. Please, omega cannot multiply omega. This is a function of a function. Omega t is in cos, so you cannot multiply this thing like that. It doesn't work like that. How do we use this? Please, are you done writing this? What is here?
Nope.
No, please.
Okay, quickly do it. Give me 1 minute. I'm coming, okay? So back from commercial break. So V is equal to A omega cos omega t is the velocity function of a body in simple harmonic motion with respect to time. Now let's look at how do we use this. A body doing simple harmonic motion. A body doing simple harmonic motion. Let's take the simple pendulum. When you give a small angular displacement, theta, these are the extremes. The amplitudes occur at the extremes. This is the fixed point or the equilibrium position. Now, at the extremes, the body has a velocity of, what's the velocity at the extremes? This is another extreme. Class, what is the velocity of a body in simple harmonic motion at the extremes? Yes. Ideas. I sent you a picture. So what's the velocity of the body doing simple harmonic motion at the extremes? Eliana.
0.
0. So this is it. This over here, the body is at the equilibrium position. When I displace it, look at it. Okay. Now, when it got to one extreme, it couldn't proceed on. It stopped because the velocity, okay, is reducing as it goes. So it's like when it is moving from here, the velocity reducing. By the time it gets to the farthest it could reach, the velocity has reduced to 0, and it has to, by gravity, it has to come again. So pushed, when it's coming, increasing. By the time it gets here, it has reduced to 0. So 0 velocity. So at the extremes, V is 0. V is 0. The velocity is maximum when the body is crossing the mean point. Maximum velocity occurs at the mean point or the equilibrium position. So these are fundamental knowledge. When you are asked, you must say. So if we relate it to what we have here, these are the extremes. One extreme, another extreme. At the extreme, the velocity is 0. So 0 velocity when it's coming back, increasing. By the time it gets here, it's maximum. When it is coming back, decreasing. By the time it gets here, it's 0. Okay, when it's so that's how it works. Please, are we okay? Class, are we fine?
Yes, please.
Priscilla, are you there or you are gone?
Mr. Deputy, I'm here.
Okay. Now, we can plot a velocity function. Velocity equation with respect to time. So let's plot a velocity equation or function of a body doing simple harmonic motion with respect to time and see how that also works out. We've done for displacement for 2 cycles. Let's do it for velocity for maybe 1 cycle or more. So let's block it because this is velocity against time. So when the body moves from 0, the mean point, what is its velocity? When it comes here, what is its velocity? Coming back, and so this is one cycle. So one cycle has 4 quadrants or 4 different cycles. When it starts from here, 1, 2, 3, and 4. So it goes, the time goes with the division. So at a time 1/4t, the time for a complete oscillation, okay, is the period. That's why we are doing a quarter of the period, half of the period. Okay, so this is half of the period. Now 3/4 of the period. Then a full period. Okay, so this is the time for one cycle. Let's do it for 2 cycles. So it goes with the same time. 5/4 of the period. Three on 2 of the period. 7/4. I asked you to do this. Only one person submitted the assignment. Eliana. Eliana was the only one. Deborah, dry. Adwa, dry. Now we know.
Mr. D, I got it.
Mama, memotie.
Mr. D.
Don't mind, don't worry me. So this is for 2 cycles. Okay. Now, the velocity function V is equal to A omega cos omega t, meaning the amplitude is this. So we can have a positive amplitude A omega and then a negative amplitude minus A omega. Just as in the displacement function, y is equal to A sine omega t. A is the amplitude. Here to the maximum velocity will be this. And it can be a positive or negative. So let's do our calculations. So at t is equal to 0, meaning t is equal to 0 is here. At t is equal to 0, if the velocity function Priscilla,
Mr. Adria,
keep quiet. At t, if velocity function is this, A omega cos omega t, at t is equal to 0, what will be the velocity? Yes, if you are the professor of this, at t is equal to 0, what will be v?
Mr. Adria, the velocity will be A omega.
So it will be equal to the amplitude. Please, if you are not clear, a quick one. V is equal to A omega cos of omega is 2 pi on the period and the time is 0. So all this part goes to 0. So A omega cos 0. And what is cos 0? Cos 0 is equal to what? Cos 0 is equal to 1. So we have A omega. So at t is equal to 0, the displacement is equal to, the velocity is equal to the amplitude. Adwa Mponsa, yours is calculate at t is equal to 1/4. What will be the velocity? Adwa. Then Priscilla.
Mr. Adria,
Yours is at t is equal to half of the period. What is V? Gerard or Kenneth. Yours is at t is equal to 3 on 4 of the period. What will be the velocity? So this is for Gerard. Gerard. Now, Obi ko Nana Dubia. Uh-huh. I'm assigning work to you so that we could do it quickly. Check. Case you are now, but so quiet on the married. So, Edubia, yours is at t is equal to the period. What will be the velocity, Edubia? So give me this. When you finish, we can continue. So, Priscilla, what did you get for at the velocity at time equal to half of the period? This time. Oh, sorry. I think I gave this to Adwa. Adwa, what is your time? At quarter of the period, what's the velocity? Adwa. Adwa. Okay. At t is equal to quarter of the period, please, what's the velocity? Those
0.
of you is 0. So it will be 0. Adwa, this calculation is this. I showed you 1. So A omega cos of 2 pi on the period times t. Your time is quarter of the period. This t is what we are representing by this. So t on 4. So t and t cancels out. This is 2. So you have pi on 2. So pi on 2. And what is pi on 2 in degree? What is pi on 2 in degree? To the house, what is pi on 2 in degree?
90
90.
90. So cos 90 is 0. Simple. And so the velocity will be 0. Okay, Priscilla, at t is equal to half of the period, what's the velocity?
Yeah, I got minus now.
Minus
8.
what?
Minus AW.
So negative of the amplitude. Thank you. So this is it. Okay, 3/4 of the period. Gerard. Eh? Still on it. We also still on it. 3/4 of the period. What's the velocity? If
0.
3/4 0. What did still on it? No, 0. Let's do it. So V is equal to A omega cos omega t. At t is equal to 3/4 of the period. Okay. We have V is equal to A omega cos omega is 2 pi on t times 3 on 4 t. So t 2. So you have cos of 3 pi on 2. And what is 3 pi on 2 in degree? What is 3 pi on 2 in degree?
270 degrees.
270. And cos of 270 degree is, point your calculator, cos of 270 degree is
0.
0. So Gerard, did you have you had it?
Yes, sir.
Good. Now Edubia, What is the velocity at t is equal to the period?
I got 0.994.
Hey, how did you get 0.994?
I think
Eh,
it's
let-
1, but I got
Let's see.
So if when t is equal to 1, t is equal to
No,
4 out
t
of 4.
is not equal to 1. No. The time is equal to the period. T. Small t is equal to the period.
Sorry. T is equal to 4 out of 4. T is equal to t. Small t is equal to big T.
So look at it. So we have A omega cos of omega is 2 pi on the period. Now this time small t is equal to this. So times capital T. Please, are you okay with the substitution? So that
Yes,
this
please.
would cancel this. You have A omega
Yes,
cos.
please.
What is 2 pi? What is 2 pi in degree?
360.
So 2 pi is equal to 360 degrees. Now, punch cos of 360. What is the cos of
Mr. Dia
360?
is 1.
Cos 360 is 1. So it means that this is equal to A omega times 1. So the velocity there is actually equal to A omega. Is that okay? So it's equal to the
Mr. Dia, but
amplitude.
0.994 is 1.
Pardon?
0.994 is 1.
No, how did you manage to get 0.994 for cos 360?
So I inputted cos 2 pi directly.
And when we were doing this, you were not around. That's why. 2 pi is angular measurement in radian. In degrees, 2 pi is equal to 360. Okay, so we are changing the angle from radian to degree. That's why we change 2 pi to 360. Are you okay?
Yes, please. Thank you.
So velocity is equal to A omega. No, what we are doing isn't difficult. Oh. Not at all. You just need to understand. Okay, so what about at hello?
Sir,
Yeah.
please, can we say that when we get to where you're supposed to punch in the 3/4 pi and those things, you can just replace pi with 180 and then solve it.
Exactly. Wherever you see pi is equal to 180 degrees. Okay. So at t is equal to 5/4 of the period, what will be the velocity? Yes. Brittany, contribute. Adua, contribute. We are learning. You may get it wrong. It's part of the learning. So don't be worried getting something wrong. What did we get for velocity at time 5/4 of the period? Yes. What is the velocity at this time? At
If it's at 0.
0.
yes, so it's 0. Hilda, are you there?
Yes, please.
And now what Hilda, what on that? Okay, so what's the velocity at this time? At 3 of the period, what is the velocity?
Minus AW.
Minus AW, yes. So it tells you this time goes with a velocity of this. Then the velocity at the time t is equal to 7/4 of the period.
0.
is 0. At some point, you can even predict the trend. Then, at the time t is equal to 2 or 2 times the period, what's the velocity?
AW.
Yes. It's equal to the amplitude. Adwa. Okay, so let's join our points. Let's join our point. And this is very, very beautiful. So this is how the graph, the velocity graph of a body doing simple harmonic motion is for 2 cycles. There's it. And when you understand this, if you are given 10 cycles, you can still do it. Adelaide, are you okay? A lot of you are gone. Hello.
Please, I cannot see I can't see anything, like it's
Blurry.
not blur, like it's black, everything is black. I
Then
cannot see.
rejoin. Then rejoin. Okay.
Okay.
It's a problem from your end. As for me, I can see. Hilda, are you fine? Nanadwa,
Yes, please. Yes, Mr. Ejia.
are you okay?
Yes, please.
Adwa, Eliana, Nanadubia, are you fine?
Yes, please.
Trifina, are
Yes,
you trying?
Yes,
Trifina,
please.
okay. So you see, we've drawn it for displacement velocity. So beautiful. And so we've learned that for an oscillating body, the velocity is maximum when at the equilibrium position, and it's minimum 0 at the extremes. Okay. So this is the velocity of a simple harmonic motion with respect to time. When time changes, this is how the velocity also changes. Now, there is another dimension of velocity of a body in simple harmonic motion. With respect to time, is straight away V is equal to A omega cos omega t. But look at something. Let's assume that a question is given to you, and the question is saying, oh, okay, the displacement of a body in simple harmonic motion is a certain x centimeter from the origin or from the base point. So x centimeter. What is the velocity? So here, what they mean is that the body is here. The displacement from the fixed point to where the body is x centimeter. What and they are asking of the velocity. So what have they given to you? Here, they have given you displacement. They have given you displacement y, and they are asking of velocity. From this equation, it's like having been given time to find velocity. So at time, a quarter of the period, what is the velocity? At a time, half of the period, what's the velocity? That's what we have done. So what we've done is actually velocity in terms of time. Okay. Now, if you are given the displacement and you are asked to find the velocity, how would you find it? That's the next equation we are going to derive. Okay. Class, okay.
Okay, Mr. Adrian.
So how do we get that? Using, you see, we have y displacement is equal to a sine omega t. There are some constants you must not forget. That's the displacement equation of a body in simple harmonic motion. So if I ask you, what is the displacement equation of a body in simple harmonic motion? It must be a sine theta, sine omega t. Of course, it can be a cos omega t. Okay, but if it's cos, I'll explain later. Okay, but the general one is this. So if displacement y at any time t, there's it. Now the velocity is a omega cos omega t. These two you must understand. Now all that I'm going to do is that I'm going to play around this equation so that I can substitute y into it. Y is displacement. So I want to substitute y. So at a displacement y equal to so and so, I can find velocity. So I'm going to manipulate this to substitute y into it. So open your eyes and then let's look at what I'm going to do. Now, if I play around this and I have a out, then the square root of omega squared cos squared omega t plus, have I changed this? Have I changed this original? When I manipulate this way, have I changed the original?
No, sir.
I haven't changed anything. All right. Now, or the other way around. I think I must rather get it the other way around. This is out. A squared rather in, and I bring omega out. I haven't changed anything. I haven't changed anything because when I square, since this and this are multiplying, when I square a, I'll still have my a. When I square cos squared omega t, I'll still have this. So I haven't changed anything. Are we okay? Deborah and Co. Nanadra and Co. Now, I also know that sine squared omega t plus cos squared omega t is equal to 1. So I want to make cos squared omega t the subject here, so I can substitute it into this. So maybe this equation 1, equation 2. I want to make cos squared omega t the subject. So I have cos squared omega t is equal to 1 minus sine squared omega t. Please, are we fine? Are we fine?
Yes.
I've only made cos squared omega t the subject. Once this has been made as the subject, I'm going to substitute this into equation 1. So substitute into equation 1. So in equation 1, wherever I see cos squared omega t, I'm going to put this in. So I have V is equal to omega a squared. Now in place of cos squared omega t, I'm going to put this 1 minus sine squared omega t. All right. Then multiply through by a, which is outside the bracket. When I do that, I have v is equal to omega a times 1 a squared minus a squared sine squared omega t. Ladies and gentlemen, instead of a squared sine squared omega t, I can clear this and put all of them under a bracket sign and square it. And it will be the same thing as the earlier one. Please, are you with me? Class, are you with me?
Yes, please.
Okay. Now, can't I substitute? I have a sine omega t, which is equal to what? A sine omega t, which is equal to what?
Why?
Y, the displacement. A sine omega t is equal to this. So I can now substitute y into the equation. Eliana, are you there? Eliana. Oko Crusade. Okay. So I have a squared out, a squared minus y squared. And this is the velocity equation of a body in doing simple harmonic motion in terms of displacement. This A is the amplitude of oscillation, which is always constant. So let me continue writing here. So y b is equal to omega out a squared minus y squared is the velocity equation of a body in simple harmonic motion in terms of displacement. So with this, when they give you the displacement, the amplitude and omega are constant. I told you that a body in simple harmonic motion does so at a constant angular velocity. So omega is usually constant. The amplitude is usually constant. The displacement is what will vary. Okay. So when they give you a displacement of so and so, you can find V. Class, are we okay?
Yes.
Are we okay? Or you are not okay? Now, we use the velocity equation with respect to time to determine the velocity at the mean point and realize that it is maximum. And also realize that the velocity at the extremes is 0. We establish that. We can also establish that same thing using y. Now, at the mean point, what is the displacement of the body? If an oscillating body is at the mean point, what is the displacement y, class?
Zero.
Is 0. Please, are you okay? Because the body is at the mean point. So it's similar to this. This is an oscillating body, and the body is just here. So when the body is just at the mean point, okay, the oscillation is 0. Right, the displacement y is equal to 0. So using the equation, if y is equal to 0, then v is equal to omega square root of a squared minus 0. 0 squared. 0 squared is still 0. So we have v is equal to omega times the square root of a squared. And the square root of a squared is equal to a. So v is equal to omega a. And this also tells us that the maximum velocity occurs at the mean point where y is equal to 0. So for an oscillating body, for a body in simple harmonic motion, maximum velocity occur at the mean point, or at the equilibrium position where displacement y is equal to 0. Please, are we fine? Are we fine? So here to maximum velocity occur at the mean point, and the expression for maximum velocity, V maximum, is equal to omega A. Now, when the body displaces to the extreme, at the extreme, okay, the body displaces and then comes to the extreme, either here or here. Now, at the extreme, the displacement y is equal to, yes, at the extreme, the displacement y is equal to what? Nanadwa. Hey, people are going, So at the extremes, the displacement y is equal to the amplitude. So at the extreme, y is equal to the amplitude. So when the body gets to the extreme, the displacement is equal to the amplitude. Now look at this. We are using the equation to confirm that. Edubia, what is the velocity of the oscillating body at the extremes? What is the velocity at the extremes, Edubia?
The velocity of the oscillating body at
The extremes. At the extremes.
And it would be V is equal to AW.
So
Okay,
no,
sorry.
what is the value of the velocity
V.
at the extremes? Nana, if you are at the extremes, what is the velocity?
V is equal to WA.
No,
0.
it's 0.
Why?
At the extremes, when I was demonstrating this, I told you that when the body gets to the extremes, okay, if there's the extreme, when it gets there, it could come back because V is equal to 0 over there. So V is equal to, at every extreme, when the body returns, when it gets here and returns, it means over here, the velocity at that point is equal to 0. So the velocity of the oscillating body at the extremes is always equal to 0. So at the extreme, y is equal. Hello.
Please, the displacement is also equal to 0.
No, the displacement is not equal to 0. At the extremes, the displacement is equal to the amplitude maximum. So that's why we call the amplitude as the maximum displacement. Okay. Now that's what I've done here. at the extremes, there are two extremes. So at the extremes, the displacement y is equal to the amplitude. But the velocity, we are going to prove that the velocity at the extreme is equal to 0 using the equation, using this velocity equation in terms of displacement. Are we okay?
Yes,
Are
please.
we okay? So if y is equal to a at the extremes, then using the equation v is equal to omega times the square root of a squared minus, at the extremes, y is equal to a. So in place of y here, we are going to substitute a, because at the extreme, displacement is equal to the amplitude. So y is equal to a. So a squared. Are we okay? So if a squared, look at it. You have a squared minus another a squared, then the square root of it. So you have v is equal to omega square root of 0. Now, what is the square root of 0? Is 0. 0 times omega is 0. So v is equal to 0. Confirming that the velocity of the oscillating body at the extremes is equal to 0. Class, are we okay?
Yes, sir.
Yes.
Yes, please.
Yes. So these are facts you must understand. Okay. One, the displacement is at the extremes is maximum. That's why we call the displacement at the extreme as the amplitude. The amplitude is the maximum displacement. Now, when it comes to velocity, velocity of a body in simple harmonic motion is maximum at the equilibrium position, when the body is crossing the equilibrium position or the fixed point. So it's maximum at the equilibrium position, and its formula for calculating it, relation is given by v is equal to omega a. So maximum velocity is equal to v is equal to omega a. Then the velocity at the extremes, where we have the maximum displacement, is always minimum, and its value, this minimum value is 0. So the minimum velocity occurs at the extremes. Let's solve a question. Then I think we'll look at the acceleration another time. The way people are just joining and unjoining, it tells me tiredness or whatever is there. So, okay. I'm giving you a question, so get ready to put it down. Are you ready?
Yes, sir.
Okay, so an object attached to a spring, oscillates in the vertical plane an object attached to a spring oscillates in a vertical plane about a rest position O, that is equilibrium position, about a rest position O with an angular velocity of 4 radian per second. With an angular velocity of 4 radian per second. with an angular velocity of 4 radian per second and amplitude 10 centimeter. The amplitude is 10 centimeter. Between extreme positions A and B, capital A and B. So an object attached to a
Mr.
spring
Diate, can you repeat the last statement?
An object attached to a spring oscillates in the vertical plane about a rest position O with an angular velocity 4 radian per second. With an angular velocity 4 radian per second and amplitude 10 centimeter. And amplitude 10 centimeter between extreme positions A and B. Between extreme positions A and B, full stop. Calculate I. Calculate I. The velocity when crossing the rest position. Calculate I. The velocity when crossing the rest position. I. The velocity at the extreme ends A or B. The velocity at the extreme ends A or B. And I. And I. The velocity at a point, 6 centimeter from O. The velocity at a point 6 centimeter from O. So these are three questions. Hello.
Okay, so the first one I had 40 meters per second.
Look at it again.
So the second
Gerard,
one,
take your time and look at it. There is
okay,
some omission, so just take your time and look at it.
okay, so, but the second one is 0.
As for the second one, he said the velocity at the extreme ends, A or B. And whenever a body oscillates and gets to the extreme ends, we've just realized that the velocity at the extreme ends is equal to 0. So that is not a problem.
And then the third one I had 16.
16 what?
The 16 meters per second.
No, take your time and look through it again. No. Please give it a try. About 5 minutes will do. Maybe three would rather be fine. I started with a lot of people. Now I'm left with Adjoa, Brittany, Deborah, Eliana, Gerard, Hilda, Nane Dubia, Nanefua, and Trifina. So the Adelaide I saw, Kezia I saw, they are all gone. Priscilla,
Please, the first one is 0.4.
0.4 what?
0.4 meters per second.
Yes, it will be so. Yes, I think it's so. But
And
you
the last
do
one,
it. We will discuss it. So you do it.
also that I'm done with the full question.
No, what I'm saying is that because others are also looking at it. So once you have to look at it and then let's give others the time to also think through. Okay.
Okay, sir.
All right, so let's look at the question. So our number is reducing day by day. Ajua, Ajua, are you there? Edubia,
Stadia.
what did you get for the first part of the question? Edubia is gone. Deborah, Deborah,
Mr. Dear, please, I'm still on it.
okay,
Sorry,
Brittany,
my internet failed me.
Brittany, what did you finish? Okay, I think if
Stadia.
did you finish?
No.
Hilda,
Miss
did you finish? Okay, so
Stadia.
the angular velocity is omega is 4 radian per second. Then we are also told that the amplitude is 10 centimeter. Now, the angular velocity is given in SI units. So quickly, we must change this to SI units, Gerard. So this is 0.1 meter. The question demands that we calculate the velocity when crossing the rest position. And we just learned that when the body is crossing the rest position, its velocity is maximum. So maximum velocity occur when crossing the mean point. And if maximum velocity occur when crossing the mean point, what is this relation? We realize that V max, the maximum velocity is equal to omega times the amplitude. This is the formula we had for the maximum velocity which occur at the mean point. So V max, let me bring it down. I think the reflection. Omega times A. Now what is omega? 4. The amplitude is 10 centimeter, but we change it to meter. So 1 on 10. So this is equal to 0.4 meter per second. The maximum velocity is equal to 0.4 meter per second. Gerard, that's what you had. Then II. The velocity at the extreme ends A or B. We just established that at the extremes, the velocity, the minimum velocity occur there. And this minimum velocity is 0. So, calculate. We won't calculate. V is equal to 0. Or if you want to calculate, then V is equal to omega times the square root of a squared minus y squared. What is a? A is equal to, at the extremes, the displacement y is equal to the amplitude. So v is equal to omega times a squared minus another a squared. This is 4 radians per second. The amplitude is 0.1. So 0.1 squared minus another 0.1 squared. This is 0. So what we have within the bracket is zeros. Hence, v is equal to 0 at the mean point. Then I. The I question is demanding the velocity at the point 6 centimeter from O. So when the displacement y is equal to 6 centimeter from the equilibrium position or the mean point O, what is the displacement? That's what we are looking for. So we have v is equal to omega, which is 4, times the amplitude, which is 0.1 squared. Now we are talking about a displacement of 6 centimeter from O. And let's change 6 centimeter to centimeter. If I change 6 centimeter to centimeter for me,
What?
change 6 centimeter to meter. 6 centimeter to meter.
0.6.
No,
0.06.
you divide by
0.0.
100. So 0.06 squared. And this must give you 0.32 meter per second. Calculate it. 0.32 meter per second. So that is it with your velocity there. So these are simple. As we move on, I'll give you challenging questions, but I think we have to break for today. So as we move on in treating SHM, there are other aspects we have to learn. I'll give you more challenging questions, but that is it. It's not so difficult. All right. Any question? Do you have any question?
Sir,
Gerard, I'm listening.
I don't have a question.
Okay. So if no question, then we call it an evening. We'll end here and then continue another time. Okay. A class of 15 people. We are 8 or 7. Okay, so good night to all of you. Bye-bye.
Good night.
I said.
Okay.